In the world of surface texture, there's a particular graph that is used to help us describe the shape of a surface. So if I have a segment of surface here, we're going to create this particular graph. Now this graph is called the material ratio curve in standards. Historically, it's been called things like the bearing area curve or the bearing ratio curve. In fact, it's often called by the name of the authors, and it's referred to as the Abbott-Firestone curve. Now this particular graph that I'm going to make over here represents how much material we encounter as we slice our way through the surface. So for example, if I were to slice through this surface somewhere just above the mean line here, I'd be cutting material through this red section, and then I might cut material a little bit here and a little bit more here, and I'll be cutting through material part of the time and cutting through air the rest of the time. So what we are doing when we generate the material ratio curve is exactly that. What is the ratio of material to air at this particular location? So if I sliced it at that depth and sent that depth over here to this curve, I would see that I'm cutting material maybe 20-25% of the time at this particular depth, and I would plot a point at 20 or 25% along this axis that goes from 0 to 100. So at that depth, I have some amount of material, maybe 25%. At the very top of the surface, if I were to slice, I would have 0% material, and at the very bottom, if I were to slice, I would have 100% material. So the material ratio curve is going to be made by slicing at all of the possible levels. And at this particular level, we see that I'm cutting metal or cutting material, depending on what you're cutting, a lot of the time. This might be 90% of the time I'm cutting through material. So we're creating a curve by slicing through this profile at various depths. And this curve will take on a shape that sort of resembles the surface itself. The shape of the curve in this case is kind of pointed at the top, representing the peaks we have at the top, and then there are a few valleys hanging around the bottom, representing this part of the curve. So the material ratio curve is a way of kind of compiling the surface into a shape. Now, if we had a surface that was extremely plateaued, for example, if I had a surface that was very smooth on top with some valleys, the curve will take on that shape. I will slice a little ways down into this surface, and I'm already at 80 or 90% material, and we would start at the top with 0, and the curve would be very flat on top, very much like how the surface is flat on top, and then the surface will eventually roll into the valleys where we don't add material very quickly. Similarly, if I had a surface that was turned or maybe milled in some way to have scallops in it, the material ratio curve will take on a very different shape. In this case, the curve will have 0% and will go a long ways down into the surface before we actually start getting into any significant amount of material. So the material ratio curve is a way of representing at varying depths how much material do I encounter from 0 to 100%. Now we're going to use this curve, we're going to use the shape of this curve to create some parameters. So this will serve as the basis for some of the parameters you'll be seeing throughout the library.